In these videos, we're going to look at an example of an investigation that leads us through both informal inductive reasoning, where we look at patterns and try to make guesses, and then going back and proving those with official mathematical induction. So it's based on a PDF that's, I'll have the link in the description, and we're looking at that PDF right now. Well, we're looking at what generates the PDF. And I'm going to go through, and in little bits in each of the videos, we're going to go through and do the problems. The best way to do this is to look at the PDF and try to do as much as possible, and then just come to these for hints or answers. So we're looking at guessing and finding patterns with sequences. And I like to do this because there's just one basic idea that gets you a lot of cool stuff. Just taking any sequence, maybe call it x sub n just for temporary notation, and we're just going to look at the partial sums of that sequence, and we're going to repeat that. So another way to say it is we're going to keep track of the running totals of the values of a sequence, and then we're going to do that to that new sequence, and then do it again, and do it again. Okay, so we could have a sequence xn, and then we need a name for our new sequence. Let's call it Sn for the sums. And it turns out to work. We get a nicer punchline, a cleaner punchline, and it works out better to connect with other mathematical ideas. If we start labeling our sequences with term number 0, which is actually a very, very standard mathematical idea, and we're going to say that the running total at stage n, so S sub n, is only going to take the terms in x from the 0th term up to the n minus 1 term. So to make that very concrete, let's look at this example. So here is just n. So remember, n, when you have a sequence, the n's are just the labels, just to keep track of which term you're at. And what's interesting is the actual number, the value of that sequence. So these are sort of the inputs of the function, that's the outputs of the function. And this is where the action happens. So let's suppose that we just have the sequence that's all the odd numbers. The 0th term, let's say, starts at 1. And then the first term is 3, the 2 term is 5, the 3 term is 7, etc. Okay, and here's the idea with the sums. Let's skip this first one just for a minute. The first term, the n equals 1 term of the sum, says sum up to, but not including that one in this sequence, so that's just going to be 1. The second term says sum up to, but not including that term in the xn sequence. It's 1 plus 3, which gives you 4. Next term is going to be 1 plus 3 plus 5, which is 9. The next term is you're going to sum. So we're just taking the running total, 1 and 1 plus 3, 1 plus 3 plus 5, 1 plus 3 plus 5 is 7. And it's just this is a little bit of a weird convention that we're not including the current term. It's everything in the past. And why 0 here? Well, it's because there's no sum. There's no terms that we're summing up. And so we're just going to say, well, if you don't sum anything up, you're going to default to 0. It's like saying 0 times anything is 0. So there's a nice little fact already here, which is not what I'm focusing on here, which is these are all the squares: 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. Well, that's kind of cool. I'm not focusing on it because that's right in the textbook for the number theory class. And it's a very, very standard result, and you can prove that by induction, certainly. But we're going to focus on some other stuff to prove by induction. The sum of the first n consecutive odd numbers is just n squared. Okay. So if you want to look at it with summation notation, or a little bit more algebraically, S sub n is defined to be x sub 0 plus x sub 1 all the way through xn minus 1, but not including xn, because it's going to work out better that way eventually. And if you want summation notation for that, which packages it up more efficiently, but can be a little bit harder to deal with, and I always tell my students, don't be afraid to unpack summation notation if you don't like it. It's the sum starting at k equals 0, because that's where we're starting all of our sequences here, up to n minus 1 of all the xk. So it just means sum all the xk's from this starting point to this ending point. Okay. And then here's a note about we're always going to have, these guys are always going to start with 0 pretty much. Okay, so that's the context. And the start of the investigation is we're going to start with a really, really simple sequence, and we're going to take running totals of that guy, and then we're going to take running totals of that one, etc., etc. Okay, so this is definitely where you want to stop and do some stuff yourself. It's really just calculation for a little while, or a lot of it's calculation, but it's an alternation between calculation and trying to find patterns. Okay, so we're going to take the boring sequence with all ones that goes on forever, but I'm only going to chop it off at 8, so because I don't want to use an infinite piece of paper. And we're just going to take the running totals of that. So you want to take the running totals of the 1 sequence to get the b's. And what else do I ask? Oh yeah, what kind of sequence and what is the closed formula? Okay, so I'll put this in this video. I won't switch to a new video yet, but this is a good time to pause the video and try it out, and then you can make sure that you're on the right track when you come back to the video. So it starts with 0. Oh, it's going to come out not in math mode, but that's okay. Then 1, because this term, just 1 summed by itself, is just going to give me 1. 1 plus 1 is 2. Surprise, surprise. 1 plus 1 plus 1 is 3. 1 plus 1 plus 1 is 4. So this is just like if you're paid $1 every day, well, then you're pretty poor. But if you're paid $1 every day and you keep track of your bank account, then that's just going to go up linearly like this. Or in other words, that's what's called an arithmetic sequence. It's the most basic, cool example of an arithmetic sequence, just the consecutive integers. The common difference between each term is just equal to 1. Okay, so there we go. There's b sub n, and of course, a formula for b sub n is just n. That's it. If you just look at it, they match exactly. On day 0, you have nothing in your bank account because you haven't been paid this dollar yet. On day 1, you have $1 because you got paid that dollar yesterday. You haven't gotten paid this one. And then after day 2, you got 2. If you have after day 3, you got 3 in your bank account. Okay, so that's just a nice little warm up. Now it starts to get interesting. Let's let the third column of the table, or the C sequence column, be the running total of the B's. Okay, so now again, you can just do this by computation. Let me just do this, and then we'll switch to the next video. So 0 again. Okay. Now here's something. I'm totaling up these guys. This one is supposed to be the total of this column only through here. So that's actually going to be another 0. So it takes a while to get started. Okay. Now this is supposed to be the total of these two, which is 1. Now the total of 1 and 2, or 0, 1, and 2, which is 3. 1 plus 2 plus 3, which is 6. 1 plus 2 plus 3 plus 4, which is 10. And then 15, 21, 28. And it's going to keep going, but that's enough for now. Okay. So now the thing to think about is any kind of patterns you can find. Anything about how we did that calculation. I know it's pretty simple-minded so far, but there's actually a lot you can discover right now about this C sub n sequence if you don't know it already, which you might well, because if you know about arithmetic sequences, then you've probably been exposed to the formula for the sum of an arithmetic sequence. Okay, good place to stop.